Today's topics is order and molecularity, effect of temperature, effect of catalyst, methods to determine order of reaction of chemical kinetics. Let us know rate law or rate expression and rate constant. The expression which relates the rate of reaction to concentration of the reactant is known as rate law. I am repeating again, the expression which relates of rate of reaction to concentration of the reactants is known as rate law. It is also called as rate equation or rate expression. Consider a general reaction. The rate expression for a given reaction can be written as follows. Rate of reaction is proportional to product of concentrations of reactants powered by the number of moles of that particular reactants. Rate of reaction is equal to K into product of concentrations of reactants powered by the number of moles. Here K is to be considered as rate constant. From this rate expression, we can obtain order of reaction. Here order of reaction is equal to sum of the exponents present in the rate expression. Here in the given rate expression, the exponents are x and y. So order of that particular reaction is equal to x plus y. If you assume that x is equal to 1, y is equal to 1, then order of reaction is equal to 2. Thus, rate law is the expression in which reaction rate is given in terms of molar concentration of reactants, with each term raised to some power, which may or may not be same as the stoichiometric coefficient of the reacting species in a balanced chemical equation. This is just explanation for previous expression. Rate constant of a chemical reaction may be defined as the reaction rate when the concentration of each reactant is unity. So this means, see here above, when the concentration of A is equal to concentration of B is equal to 1 mole per liter. Okay, so now here unity means 1. So then we can define the rate constant as I told previously. The value of rate constant is definite and constant for a particular reaction at given temperature. So note down that the rate constant is temperature dependent. Rate constant is independent of concentration of reactants. It depends only upon temperatures and presence of catalyst. These are very very important points. The value of rate constant is definite at and constant for a particular reaction at given temperature. Rate constant is independent of concentration of reactants and dependent of temperature and presence of catalyst. Order of reaction. The sum of powers of the concentration of the reactants in the rate law expression is called the order of that chemical reaction. For a given chemical reaction, the rate of reaction can be expressed as follows, that is, K into A to the power of X, B to the power of Y. X is equal to order of reaction with respect to A. Y is equal to order of reaction with respect to B. Overall order of reaction is equal to X plus Y. Keep in mind, the order of a reaction can be 0, 1, 2, 3, and even a fraction. And in some cases, order may be the negative value. Depending upon order of reaction, reactions are termed as zero order reaction, first order reaction, second order reaction. A zero order reaction means that the rate of reaction is independent of the concentration of the reactants. This is important definition. A zero order reaction means that the rate of reaction is independent of the concentration of the reactants. Order of a reaction cannot be predicted by merely looking at a balanced chemical equation. That is theoretically, but must be determined experimentally. Keep in mind, one cannot find exact order by observing the balanced equation. We should go for experimental methods to determine the order of particular reaction. Molecularity of a reaction. Molecularity of a reaction is simply the number of reacting species involving in an elementary reaction which must collide simultaneously. Molecularity of a reaction is simply the number of reacting species involving in an elementary reaction which must collide simultaneously. Let us consider the following reactions. So, here, if there is only one mole reactant molecule, then it is said to be unimolecular reaction. If there is 2 moles, bimolecular. If there is 3 moles, trimolecular. Molecularity in case of complex reactions. Molecularity of a complex reaction has no meaning. Actually, a complex reaction is the series of two or more elementary reactions, and thus it completes in several steps. The slowest step or slowest reaction determines the rate of the reaction. Hence, we find out the molecularity of the slowest elementary reaction of a complex reaction, which is in general similar to the overall order of complex reaction. These are the differences between molecularity of reaction and order of the reaction. Integrated rate equations for different order of reactions. Here in this slide we have shown the derivation of integrated rate equation for a zero order reaction. So here let us see, for zero order reaction K is equal to initial concentration minus final concentration divided by T. This is the plot obtained from integrated rate equation for a zero order reaction. Integrated rate equation for first order reaction. Here, this can be derived as follows. Let us see the final equation obtained by integrating K is equal to 2.303 by T log base 10 initial concentration divided by final concentration. This is integrated equation for rate constant of first order reaction. This is the graph obtained for the integrated rate equation for rate constant of first order reaction. Half life of the reaction. As we know that the time required for utilization or consuming of half of the initial concentration of the reactant is said to be half life. The time required for consuming half of the initial concentration of the reactant is said to be half life. Here, half life for a first order reaction is derived. Thus, for a first order reaction, half life period is constant. It does not depend upon the initial concentration of the reactants. Pseudo unimolecular reactions. The reactions which are not truly of the first order, but under certain conditions, reactions becomes that of first order, are called pseudo unimolecular reactions. Let us take example as ester hydrolysis. Here in this reaction, the appearance of the reaction seems to be second order. But being in this particular reaction, the H2O is to be taken in excess. So the excess concentrations does not influence the rate of reactions. We can ignore the excess concentrations during writing the rate expression. So only the ester should be mentioned in rate equation. So the order of this reaction is 1. So it is to be considered as pseudo unimolecular reaction. Here there are different methods for determining the order of the reaction. Number 1, integrated method. The equation which gives a constant value of K decide the order of reaction. In this method, we have to derive different values from the experiment, and then we have to substitute the integrated equation for rate constant. If the K value is constant, then we can decide the order of a reaction. Suppose if you substitute the values in the integrated equation for rate constant of first order reaction, if you can get the constant value of K, the reaction you performed is considered as first order reaction. Graphical method. The data obtained from the experiment are plotted according to different integrated rate equations, so as to yield a straight line. Slope gives the value of rate constant. Initial rate method. The concentration of one of the reactant is varied. This is said to be initial rate method. Half-life method. In this method, we plot half-life of the reactant versus concentration of the reactant. These are graphical representations for concentrations of integrated rate equations versus time. Initial rate method I am explaining here. This method involves the determination of the order of each reactant separately. To determine the order of particular reactant, its concentration is varied, keeping the concentration of other reactant constant. In every experiment, we determine the initial rate of the reaction and observe the dependence of rate on the particular reactant. Let us see if you perform this for A plus B gives rise to C plus D reaction. If you want to determine the order with respect to A, you should keep the concentration of B as constant. If you want to determine the order with respect to B, A should be keep constant. Integrated method. In this method, we put the data into the integrated form of rate loss and calculate the values of rate constants for different kinetics of the reaction. The order of reaction is that one for which the value of rate constant is constant. Some points regarding activation energy. You know that activation energy means the energy required for a molecule to participate in the reaction. I am repeating again. The activation energy can be defined as the energy required for a reactant molecule to participate in the chemical reaction. Activation energy abbreviates as EA. EA is always positive. The larger the value of activation energy, the slower the rate of reaction at a given temperature. The larger value of EA, the steeper the slope. A high activation energy corresponds to a reaction rate that is very sensitive to the temperature. Effect of temperature on rate of chemical reaction. Here, this can be explained by Arrhenius equation. The temperature dependence of the rate of a chemical reaction can be accurately explained. A is frequency factor or Arrhenius constant. EA is activation energy. This is the plot we can obtain. The effect of temperature on rate of chemical reaction. Here, this is the derivation. It is based on taking logarithms to the Arrhenius equation. Effect of temperature on rate of chemical reaction can be studied by using these plots. Here let us see the blue curve represents T and T1, the red color curve represents T2. So here let us see here T2 is greater than T1. Catalyst. Catalyst is a substance that changes the rate of reaction without being consumed in the reaction. So, in other words, we can define catalyst, a substance which can change the rate of reaction without involving in a chemical reaction. These four are the characteristics of catalyst. It provides an easier way to react. Lower activation energy is enough in presence of catalyst. Still make the same products. Enzymes are biological catalysts. Here, the substance which can decrease the rate of reaction is called as inhibitor. Inhibitor are also called as a negative catalyst. This plot reveals how the catalyst can change the reaction rate. Here, red color curve indicates the activation energy required for completion of a reaction in absence of catalyst. And the orange color curve represent the activation energy required for completion of the reaction in presence of catalyst. Let us consider in absence of catalyst activation energy is EA1 and the activation energy in presence of catalyst is EA2. EA2 always less than EA1. Rate law and mechanism. A mechanism is a collection of elementary steps devised to explain the reaction in view of the observed rate law. Here, the rate law for the given reaction has written. Can the elementary reaction be the same as the overall reaction? This is the question here. If they were the same, the rate law would have been like this. Therefore, the overall reaction is not an elementary reaction. Rate determination step in a mechanism. The slowest step of a reaction is to be considered as rate determination step. The rate determining step is the slowest elementary step in a mechanism. And the rate law for this step is the rate law for the overall reaction. Based on this, we can determine the molecularity as well as order of the reaction also. Steady state approximation. The steady state approximation is a general method for deriving rate laws when the relative speed cannot be identified. It is based on the assumption that the concentration of the intermediate is constant. Thank you. Happy learning.